welcome back. Today, myself, I am Sai Krishna. Today, I will be continuing with my class, lecture 3. We will be discussing regarding spacecraft, orbit, and multistage rockets. And we will be continuing the previous topic, which is related to your transfer orbits. Now, let us reiterate what we have discussed in the last class, that is transfer orbits, so that it will be easier as to understand the furthermore topics, which includes escape velocities as well as other multistage rockets. Now, in the previous class, what we have discussed is basically these three equations as well as the graph. Regarding the same graph, we will be discussing a small concept, which is nothing but your transfer orbits. Now, let us consider a orbit in which planet rotates, particularly Earth, right? First, what happens under your transfer orbits? You will be parking a vehicle from one of the nearby orbits or low Earth orbit, right? Which is around approximately 500 kilometers, for example, right? This 500 kilometers, you will be parking a small satellite, let's say call it as S, in an orbit around Earth, right? And it will be moving at certain velocity, particularly orbital velocity, with some circular orbit. Now, in order to transfer this to a higher order circular orbit, or else to an orbit of some 1500 kilometer, right? We need to transfer from 500 to 1500 kilometer. What happens, as we discussed earlier, in order to directly transfer satellite from Earth surface to 1500, it will be costing us more amount of energy in terms of creating of complete rocket as well as using high amount of propellants. Now, it will be easy for us to just transfer the same directly to a 500 kilometer low Earth orbit, then transfer it to another, or should increase its altitude by another 1000 kilometers to reach our final altitude. Now, in this, based on the previous class, what we have discussed, the same outcomes from escape trajectory, we just need only 1.414 times the velocity in order to remain, or in order to increase your velocity to an escape trajectory. Now, based on the same, what we will do, as we know, every orbit will have apogee and perigee, and for a circular orbit, these two would be nearly same, right? As they are nearly same, what we will be doing, at the perigee, we will be adding more amount of velocity in order to increase the apogee more, right? For example, we will consider this point as perigee and this as apogee, and this will be your orbit 1. Let me just take it over, right? Now, at perigee, we will increase more amount of velocity so that the orbit shifts itself to an elliptical path, right? So that your A shifts onto this. Furthermore, let's say after first burn or certain addition of velocity, what happens? The perigee will remain approximately same. Rather than 1 or 2 kilometers here or there, it will be same. But the apogee will be much farther than the Earth, right? Now, as we have read earlier, or we have studied in the previous class, what happens during the satellite passes from perigee to apogee, the kinetic energy decreases, whereas potential energy increases, right? Again, from apogee to perigee, what happens? Your kinetic energy, particularly velocity, increases and potential energy decreases because it is the lowest point among the whole orbit. Now, afterwards, if you want to circularize, or if you want to further increase the apogee to your desired altitude, what happens again at the next pass? The satellite is supposed to add another second velocity, which increases or which forces it to increase its apogee by certain more distance, right? And this process adds up till the apogee reaches to your 1500 kilometers or the desired altitude. Now, it is in highly elliptical orbit where the energies transfer will be too frequent, right? In order to stabilize this, what we'll be doing? We will be performing a circularization burn, right? Let me just cancel it out. Now, in order to circularize, what happens? We are supposed to increase this perigee to an altitude equivalent to your apogee, so that the orbit will be circular in nature and the orbital energy at that altitude would remain same. Now, in order to do this, what we'll be doing? We will be let the time take its time to let the satellite to move till the point of apogee, right? And at the point of apogee, you will be adding more velocity. You will be adding more velocity to increase its perigee to a certain distance or certain altitude. Now, at a point where the apogee and perigee are near to equal, we will be ending the addition of the velocity so that the orbital would be maintained circular, right? Now, the circular orbital is most probably circular, only a difference of 1 or 2 kilometers, but the energy will be remaining at the same altitude. Now, this, in order to transfer from the lower orbit to higher orbit, whatever the elliptical paths we have taken are called elliptical transfer orbits, right? And in what way we are supposed to add the velocities that are needed will be determined based on the orbits from which we are shifting onto, right? From which point to which point. Now, next we will be discussing regarding the launch trajectories. Now, what do you mean by launch trajectory? Is the path. Trajectory is nothing but the path followed by a rocket. Now, launch is particularly related to your rocket. Now, based on the type of path you are taking, you will be minimizing the energy expenditure, right? For example, let's say you want to send your rocket or satellite or payload to a certain level of orbit, particularly let's say our same example, 500 kilometer, right? We are required to send a payload to a 500 kilometer orbit, and what is the energy or what is the volume of energy that is required or expelled by the rocket in order to maintain this 500 kilometer of energy or the payload to 500 kilometer of height. Now, in order to minimize that, what we will be doing? It would be better to launch in a horizontal direction, as the earth is flat. Let us discuss the same here. If I'm considering this as my earth, right? Now, what it says basically to launch in a horizontal direction. Now, from the earth surface, this will be your vertical and this will be your horizontal, right? There are two ways. In order to maintain an orbit, what happens at the end point, the orbit is always horizontal to your earth surface. It means concentrate. Now, in order to minimize the energy that is spent to reach out to a certain orbit, what you are doing? You want to launch it horizontally. Now, in this case, what happens? Rather than launching it horizontally, right? The launch point being as on a circular orbit at zero altitude. Now, the velocity of the spacecraft at rest on a surface is wrong for a circular orbit because it would be hovering above the ground, which is very similar to if you are launching it on V. Now, during a burn, right? During a burn, particularly a rocket burn, significant vertical component velocity is needed, as well as horizontal velocity is gained. Let me explain. You need energy to be increased along V as well as along H, right? For that reason, where atmospheric interference is a significant problem, where the density of air drops rapidly with height, as well as the velocity of spacecraft is also large, and the drag is proportional to the square of the velocity, and below 200 kilometers, and there is sufficient drag enough to make an orbit. So, any orbit, preliminary orbit under low Earth conditions, what we need is basically an orbit above 500 kilometers, because anything below that, you will be having atmosphere that will cause a significant aerodynamic drag onto your payload or any satellite, that again decays an orbit. The orbital decay we will be studying further and better. Now, a significant proportion of stored chemical energy has to be used to raise the spacecraft above the atmosphere or above 500 kilometers. So, atmospheric drag, which slows down the rocket to a lower atmospheric orbit, which again decays the orbit and makes it to free fall. Now, for this reason, any spacecraft are launched vertically at first, and as soon as the height has been gained, then the drag in the dense lower, particularly atmosphere, is minimized because the rocket is not moving very fast. Let us understand this bit. Let's say this is my Earth, right? Onto the Earth up to 200 kilometer, and this is my orbit of 500 kilometer, right? Now, what happens under this? Whenever you are launching a surface, you are launching a rocket, it will be always vertical to your Earth surface, right? Now, whenever you are launching, what we will be doing? We will be separating zones under basis of their air densities, right? This air density will be higher towards the surface of the Earth, whereas lower away from the Earth, right? Now, as in order to reduce the drag exerted onto our rocket vehicle, what we'll be doing? We'll be launching this rocket till a point in vertical direction in order to gain the height, which is my vertical component, right? Now, after attaining certain height or certain altitude, what we'll be doing? We will be tilting it a bit in the direction of my orbit, tilting a bit to increase its horizontal component, right? That is, once the densest part of the atmosphere is passed, which is around 30 km, a more inclined trajectory can be followed towards the surface of my Earth. Now, it cannot be completely horizontal because the velocity is not high enough if the rocket is completely inclined, particularly inclined to my Earth's surface. There is no sufficient velocity to keep it maintained at that particular height or altitude. So, in order to recover that, what we will be doing? We will be tilting it around 1 to 2 degrees per kilometer. Sorry, not per kilometer, per 10 kilometers. That the aircraft travels. Now, based on which, and this tilt angle might be varied according to the type of launches we are taking, and based on their capabilities to gain certain height. Now, after which, what happens? At sufficient velocity, it is reached for an elliptical orbit, right? Let's continue the same. Now, this is my rocket that is being flying through the atmosphere, right? Then, and this will be my path. If I am pushing out through, and this will be my apogee, right? Now, in this case, we are not yet onto the launch. We are in the progress of launch, right? And this is from Earth surface, launch site, and this is for impact site. Why I am talking about impact is basically the perigee doesn't exist till time, right? In order to have a clear perigee, you are supposed to be in a complete orbit to say that my nearest point towards the Earth's surface is my perigee. Now, in my case, particularly during the launch, after sufficient velocity is been attained, an elliptical trajectory, and this is my elliptical trajectory in which you can continue the same elliptical trajectory in order to curve an imaginary curve that will be passing through the Earth, basically. So, as we know, as the vehicle comes towards the Earth's surface, it will be getting heated up and burnt up. So, we will take it apart. We will just not stick to it now. Desired altitude to be followed, and the spacecraft then coasts. As the burn goes on, what happens? This aircraft will shut off its engines or cut off its engines, so that with whatever the velocity that it has attained, that will be the maximum altitude that it can go, which is apogee, right? And now in this case, you are adding small component of horizontal and a large component of velocity, right, during this phase. And at this point, you will be having large component of velocity and lowest component of horizontal. So now, from the same thing, what happens? At apogee, a further horizontal acceleration is needed to enter a circular orbit. Not only circular, any orbit. So, while the rocket reaches the apogee, what we will do? We will basically reignite those engines to add a significant amount of horizontal component, right? Let me just, right, a significant amount of horizontal component of the velocity, particularly in terms of acceleration of the rocket vehicle, is added at the apogee to maintain a circular orbit. And during the launch, the velocity is never high enough to attain a circular orbit, but at an intermediate altitude, which is at the apogee, it only occurs after the final injection has taken place. And intermediate orbits would require a still larger horizontal velocity because of the inverse dependence on velocity of radius. Now, thus, the motion of the rocket before the final injection is along the trajectory is always steeper than the free space ellipse. And if it intersects the Earth's surface, we know what happens. And the non-optimum nature of the launch trajectory compared with the transfer ellipse means that a good deal of energy has been lost to Earth's gravitational field. Now, there is a small additional velocity component that we are supposed to take care, which is nothing but on an Earth. Now, what we have discussed till now is on Earth. We are putting up rocket vertically and we are launching it through to space. Now, what we are supposed to know is that this whole Earth is also rotating at certain speed. We'll discuss that. Now, small additional component of velocity which can be gained by the rotation of Earth, right? And a spacecraft that in orbits responds to the gravitational field as if the mass of the Earth were concentrated at its center, right? If an object is around here, it will be rotating along the center of my Earth. Now, there is no means for rotation of Earth to affect the motion of orbiting satellite, because you are not pulling your satellite by an imaginary string or something, but it is in its place due to the gravitational field of the Earth. Now, from the frame of reference of the satellite which is in orbit, the rotation of Earth's surface is seen as the real velocity, the velocity at which it is moving. Now, the velocity of Earth's surface at the launch site, any launch site, adds algebraically to the velocity of the satellite. Now, the effect depends on the inclination of the orbit and the direction of motion of the satellite in its orbit. Let us discuss this. Let's say, this is my Earth, right? This is my equator. These are my pole, north as well as south, right? And my launch site is somewhere around here. Let's take it as India's Sriharikota, right? Sorry. Now, let us understand this. The effect of this depends on the inclination of orbits. Let's say whenever you are adding up, what we have discussed previously is, as the Earth rotates, surface rotates, what happens? Initially, a rocket which you are supposed to launch vertically will be adding up a small component of the Earth's rotation in surface velocity, so that the trajectory will move, right, in this way, where as soon as it goes, the vertical component decrease, small horizontal component will also get added on, but it's not equivalent to the surface velocity that you require in order to maintain that orbit. So what we'll be doing, we'll be understanding the position in which it is affected most. Now, as we know, in any sphere, the circumferential point is the best point to have to transfer the velocity of the Earth. Now, so coming to Sriharikota, whenever you are launching a satellite, right, from Sriharikota, if you are launching, if the orbit is regarding to your Earth rotation or geosynchronous, whatever you feel like, right? Now, if the Earth is rotating in counterclockwise direction, and we are launching our rockets in the same direction of counterclockwise at some altitude at equator, right? What happens? It adds the significant amount of the Earth's rotational velocity also. Whereas, if you are launching satellites from anything above the equator or below the equator till certain limit, right? Particularly, let's say Tropic of Cancer, right? At the time, what happens? There will be a significant drop in addition of this Earth component, right? Earth's component of your velocity to the rocket. Now, whenever you are launching at poles or in form of polar orbits are nothing but the orbits which are passing through your poles, right? Now, during polar orbits, there will be no addition, right? There will be no addition of the rotational velocity of the Earth. In other way, if you are counter launching a rocket, means if a plane of an orbit is parallel to the equator, the plane of all orbits will pass through the center of the Earth, and the satellite travels from west to east direction, then the speed of Earth rotation is added to the velocity given by the rocket. Whereas, if a satellite travels from east to west, which is an opposite direction, then the speed has to be subtracted. If an orbit is at right angles to the equator, which is polar orbit, the satellite travels over the poles, and then the rotation of the speed has no effect on it, as we have discussed. Now, the magnitude effect is very simple to calculate, as the Earth rotates 24 hours once and it has a mean radius of 6,400 kilometers. Now, the surface velocity, if you are calculating, it will be around 40,212 kilometer per day, or in terms of 465 meter per second. Now, addition of this component will be somewhat significant value, not somewhat, a large significant value while considering launch vehicles, particularly launch. Now, this additional velocity can be used to increase a payload or to reduce the required mass ratio. And the majority of launch sites are located as close to the equator as possible. For example, Sriharikota. And a recent update from Sriharikota tells us that they are planning to create another launch vehicle towards the Tamil Nadu at the end of India, so that it will, as a two major advantages. First, it will be very nearer to the equator, as well as it will be eliminating Sri Lanka completely. Because during launch, as we discuss further, we are supposed to discard any harmful products, harmful stages, as we will be staging. The discarded parts will be not affected to Sriharikota. Now, if you are looking further, Sriharikota launches are somewhat altered, right? Somewhat altered in such a way that and this will be, let's say, for Sri Lanka, right? If this is the location of Sri and this will be my equator, whenever you want to launch, let's say for polar orbit under PSLV, we know PSLV is a workhorse of ISRO, and whenever you're launching, you're supposed to create a path, particularly trajectory, in a way that it should not pass over the Sri Lanka, but it should be away. Because under the launch stages, we are launching a multi-stage rocket, which is nothing but PSLV. Whenever you want to discharge, particularly leave out a stage, what happens? You will be skipping up. Particularly, you will be skipping, or you will be discarding a stage over Sri Lanka, which might affect some population as and when, because the rocket trajectory upon free fall can't be determined yet. So, for that reason, what we'll be doing, we'll be shifting our orbit or launch trajectory along it. In order to avoid this, what we'll be doing, ISRO has planned to create a newer launch port at the south of the Tamil Nadu and launch directly down, particularly for PSLV satellites. Right? This caused the trajectory path as well as the addition of the velocity of the Earth. Now, and for satellites that are launched to higher inclination or polar orbits, the effect is not very useful, as so the launch sites can be convenient at any latitude. Now, we'll discuss regarding the velocity increment that are necessary without any gravitational loss. Now, the total velocity increment required but without a gravitational loss will assume. First, let us assume a launch from Earth's surface. Earth's surface, which is equivalent to a transfer of circular orbit of the Earth via a transfer eclipse to a 500 km circular orbit. Now, let us imagine Earth's radius circular orbit would have an horizontal velocity of 7009 or 7.9 km per second, and this is the orbital velocity at 500 km, and a transfer ellipse with a perigee at the Earth's surface and apogee at 500 km altitude has a perigee velocity of 8.05 km per second, and this will be my apogee. Peri at surface, which is nothing but my this kind of path. This will be my perigee, this will be my apogee. That will be launch. Right? Now under this, the apogee velocity is 7.4 and the necessary circular velocity is 7,616. Now, the total velocity increment that is needed in order to maintain a circular orbit at 500 km. What we will be doing, we will be adding 8057, which is nothing but the perigee velocity. 7616 is the necessary circular velocity of the orbit, and we will be subtracting this apogee velocity. We will be getting a total velocity of 8203. Now, basic understanding, the velocity cost of the launch over and above the needed circular orbit injection at 500 km is 587 meter per second. Now, this would be true if all the velocity could be given to the rocket all at once, as there was no atmosphere. But there is a gravitational loss which is included due to an extra allowance of velocity. That is, due to the atmospheric drag and gravity pull while launch. Right? Now, that particularly depends on the trajectory. An approximate value, what we had discussed previously, which is 587, is the approximate value, and the total velocity increment required is 8700. And what is the total velocity increment? 8200. Now, there is a distinction between a velocity increment and actual velocity of vehicle. Now, this actual velocity of vehicle can be calculated using my rocket equation, which shows velocity of exhaust gases, natural logarithm of initial mass by final mass, instantaneous. Now, the velocity increments is nothing but the additional velocity that is needed to maintain specified orbit. Right? The velocity increment is also calculated from rocket equation, as we have discussed, and the measure of energy expended by the rocket. And the vehicle velocity is always less than this because of the gravity loss and the energy needed. Right? Rocket equation gives us the vehicular velocity. You are supposed to add or take a factor of safety, including the gravitational loss and the energy that are needed to reach the orbital velocity. Now, in our case, the actual velocity of the vehicle in its 500 km circular orbit is 7.6. Moderate is this. While the velocity increment, considering the gravitational loss and any other atmospheric drag and all, it would be 8.7. Right? It will be around 0.9 km per second difference values. Now, the difference is the energy expended against the gravity loss as well as the potential energy due to the height. And the mass ratio for such velocity increments, especially with primitive rocket fuels giving low exhaust velocity, are too high to achieve. So, in order to recover those, what we will be doing? We will be creating, particularly Tsiolkovsky, particularly Konstantin Tsiolkovsky, have defined clearly what has proposed a concept called multistage rockets. Right? Multistage rockets. We'll discuss the multistage rockets. Now, in order, it is easy to see that discarding at least the empty fuel tanks, as we discussed earlier, under space shuttle. Under space shuttle, we will be discarding solid rocket boosters as well as fuel tank. Right? We will be discarding solid rocket motors as well as fuel tanks continuously as on when they are used. Now, based on that, it is bound to improve the performance of the rocket, whereas the thrust remains same, but as the tanks have been dropped off, the mass of the rocket is smaller and the acceleration will be greater. Now, and to calculate the effect, we can consider a rocket of a given mass ratio and divide it into two smaller rockets, where the overall mass remains same, but as on when used, we will be splitting up the rockets continuously along the trajectory that we defined. Now, a payload, which is also a part, is put into an orbit, that is nothing but a satellite, either a spacecraft, in same case. Now, that means for failure test, we need to separate the payload mass and structural mass, and the mass ratio for a single rocket can be defined. A complete rocket with payload, structural, fuel. Now, R naught, as we have discussed, is nothing but your mass ratio, and R0 suggests your initial mass. Now, in our case, Ms will be your structural, Mf will be your fuel, and P will be your payload. Now, this will be my initial mass in a single rocket. Now, at the end, what will be left out after the dropping off my payload at a certain orbit? I'll be only left with my structural, as well as after my expending of fuel, structural as well as my payload mass in an orbit. Now, by the same definition, with the structural mass separated out, means we are splitting this structural component into multiple sections. It is convenient to use as mass of fuel as either propellant or fuel in order to distinguish an MP from a payload mass. And the structural mass will include the mass of engines, rocket engines, turbo pumps, fuel tanks, as well as guidance and electronic controls. Now, in general, what we can expect, structural mass will be kept to minimum, right? And we may assume that it is a constant fraction of fuel mass, and for stages used under same fuel. By considering that, what we can do, let's consider for a single stage rocket or SSR, this will be a payload, fuel, and your fins, engines and all consist of mass of structure. Now, the same rocket has been divided into two rockets, which is nothing but halving the fuel stacked upon one over the other, which is from the same MF value are divided into half of MF under two sections, whereas the payload remains same and the rocket mass or structural mass remains same, and also equivalently the structural mass can also be divided among two separate entities. Now, this particular configuration is called a two-stage rocket, right? Whenever you are igniting a particular stage, particularly under this two-stage rocket, whenever you are igniting, as soon as you ignite, right, the first stage will completely gets burned up. First stage gets completely burned up. As soon as it gets burned, there is no use, as it's a dead equation. Now, dead part. So this particular structure, particularly the lower section, can be discarded or left off or dropped off, so that my second stage containing the payload as it is gets ignited and achieves its orbits, because now after separation of my first stage, the overall mass of the rocket decreases. As the mass decreases, my velocity of my rocket increases, right? Now, it will be happening at certain altitude based on the time that is taken by the end rocket or first stage to perform. Now, if you are putting up under two separate equations, what happens? The R1, which is nothing but the mass ratio for rocket equation 1, the mass of structure, mass of fuel and mass of propellant. These are nothing but my initial complete rocket under for stage 1. And for the final mass, what will be having? The mass of structure will remain as it is, which is a part of my rocket, and the mass of fuel will be my final one, as well as the mass of payload. The payload remains as it is, structure remains as it is. The fuel gets reduced to half. Now, this is all related to my first stage. Now, as the mass of the fuel is burned, half of the single rocket fuel load, the lower the rocket drops off, the upper rocket is ignited, which gains additional velocity, which is defined by the rocket equation. Again, in terms of second stage, the structure of mass gets halved, whereas the mass of fuel is half, and the mass of payload remains same because we are not discarding any payload. The same thing, mass of structure as mass of propellant, mass of payload remains same. This will be at the end, right? If you can get clear idea, we will discuss clearly. In a rocket, let's say if this is ground, as soon as you use under two-stage rocket, I am considering the central rocket. From the ground, as soon as you launch, what you will be getting? You will be getting till a point altitude where your first stage is completely exhausted. Now, in our case, if you are considering for this, your initial system, let's call it as intermediate and final. I am talking about two-stage rockets. Under initial, what happens? You will be having a complete structure, complete mass of the structure, mass of the fluid, mass of the fuel, as well as the mass of the payload under initial stages. Now, as soon as you enter for first stage, as soon as you exhaust your first stage, what happens? The mass at this point will be the same, whereas the fuel gets halved because you have expended fuel, right? And whereas the payload also remains same. Now, after your intermediate stage, particularly the staging part, at this point, if you're considering this as my stage 1, and this is my stage 2, under stage 2, what happens? This intermediate part, you will be removing half of the stage, right? Or first stage. You will be discarding your first stage as here. So what happens? The mass gets reduced to half, right? Of the whole total aircraft mass for the whole single two-stage rocket launcher. The complete structure gets half, whereas the fuel at the beginning will be half of the fuel as previously, and the payload remains same. The same payload remains same. But at the final stage or final orbit stage, what happens? You are expending your completely fuel, right? You are done with your fuel expansion, right? The complete fuel gets exhausted at the top. What remains basically is the same half of the structural mass and the payload. Now, based on this, what happens? This all we have done, and the final velocity of a single two-stage rocket is basically by your rocket equation, by stage, where V0 as well as V represents your initial, particularly even a single stage rocket, and V represented as two-stage rocket. What happens? V0, you will be putting M0 by M for a complete stage in this, whereas in a V two-stage rocket we will be having an additional component of the velocity, based on the type of fractions you are taking. Now, according to this equation, what we can see an advantage that V is greater than your V0, right? Instead of using a single stage rocket, it's better to use multi-stage rockets, because the overall rocket vehicle velocity will be more comparatively to your previous versions, right? And based on this, we will be, in the next class, we will be optimizing the multi-stage rockets, as well as we will be discussing few more terms related to rockets. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.